In section 4.2, we introduce finally this word integral, and this is one of the big words in calculus. And so when you hear people talking about calculus, they'll be talking about the word integral a lot. And what is the integral? Well, the integral is really that common problem that we saw last time. That was both the area problem and the distance problem. It's that problem that involves taking the height of your function and multiplying it by the base of the function and breaking the function up into a bunch of little pieces and doing height times base, and adding all those pieces together. So the definite integral has a bunch of pieces to it. One, you're breaking it up, you're breaking the range into a bunch of small sections, and then for each section you're taking the height and the distance and multiplying them, and then you're adding all those answers together. So this is really what we call the definite integral. So this part right here, when we calculate this, we're going to have a fancy word for it. We're going to call this a Riemann sum. And that's just a fancy word that says use the rectangles. So when you hear Riemann sum, and you hear if you get that letter R, and it should make you think of rectangles. So Riemann sum just says make rectangles, find the areas of each of the rectangles as you go along the way. What we know is to get the exact area, we need to take the limit of this as the n goes to infinity. And so whenever I put the limit on it, and I say what is the exact area, that's what we call the integral. And we use this fancy integral notation, and we put a and b of f of x dx. So let me talk just a little bit more about that integral notation. I'm going to write it again right here just so we can look at it a bit more clearly. Integral a b, let me erase that. Integral from a to b of f of x dx. So the integral has a bunch of pieces in it. The first is this funny kind of squiggly line. The squiggly line kind of looks like an elongated S, and that kind of makes a little bit of sense because if you notice what we're doing is we're taking a sum of all of these areas. So if it looks like an S, that's great, and you should think of the word sum. And in fact, there's a connection because if I were to rewrite this Riemann sum, I could rewrite the Riemann sum like this. I could write it with a sigma, and then I could say fxi delta x. Now, some of you are not comfortable with the sigma notation, and that's completely fine. All the sigma notation says is take this times this and add them together as you go from 1 to n. So this is a fancy way to write this down, and sigma is the Greek letter s, and now what you'll notice is our sigma has turned into an integral sign, an s-type integral sign. Our f of x stays here, and our delta x is kind of turned into a dx in some ways. Okay, so we've got this integral from a to b of f of x dx is how we write down the integral. So this is called a definite integral. Okay. The reason why it's called definite is it has these numbers telling us when to start and stop. We will have a slightly different version of this later that we give a little bit different names to. But anyway, this is a definite integral. One thing I want you to notice though about this definition is what does this definition do whenever we get like negative parts of our problem? So what if I were to do a problem like this? The integral from 0 to pi of cosine of x dx. Well, we kind of know what cosine should look like as a graph. It starts up here and comes down here and then stops, and then this is pi. So we're going to find this area. Well, what is this problem going to do? Well, it's going to draw a bunch of rectangles. But notice these rectangles are going to have positive area. But what about this rectangle here? This rectangle here will have negative area. And it's important that when we think of the integral, we can think of it as area, but areas above the x-axis are considered positive, and areas below the x-axis are considered negative. And the x-axis is always kind of that baseline that we compare everything to. So I would love it if you say, if I say what's an integral, if you say the integral is area, but it's important that you recognize it's not area, it's a positive or negative area. So what I would like even better, I'd be really happy if you can say integrals are area. It'd be even better if you realize that integrals are this sum equation, right? The integrals come from drawing bunches of little boxes. Okay, so by the way, what is this integral going to be? This integral is going to be 0 because the positive part and the negative part will cancel each other out. Okay, there's some problems like this in the book, and there's some problems like 4.5 where you're drawing areas and you're drawing pictures and you're calculating the areas of things. I'm going to go ahead and skip those. So exercise 4.5 we can skip. We're going to skip, and I'll reassign your homework, so I'll skip some of the problems in your homework as well. Okay. So the last thing we're going to do is just revisit these ideas of Riemann sums from the last section. So we're going to do a problem that looks a lot like the last section problem. So we'll do exercise 4.6, and all it says, and it is a problem that's just like what you did on the last homework. The only difference is we just changed the words. So it says find the integral from 1 to 2 of 1 over x dx using a Riemann sum with n equal to 4 and midpoints. And by the way, the textbook will often call this the midpoint rule. Whenever it says use midpoints, it'll say use the midpoint rule. So if you see that, if you see the phrase using the midpoint rule, this is exactly what it's talking about. Okay, so let's just translate this into the last section. So the last section, what would we have asked? We'd have said, well, f of x equals 1 over x. Find the area, or I would say estimate the area. The area from x equals 1 to x equals 2 using 4 rectangles and midpoints as sample points. Let me just finish there. So what I want you to say is that this is the same problem. So when you see this integral 1 to 1 over x, it's just saying estimate the area, or saying find the area from 1 to 2. And when it says use the Riemann sum, it's saying use an estimate with 4 rectangles and midpoint rule. So I'm just translating this problem into the language of the last section. Not real happy with the way that looks. All right, sorry about that. My video died in the middle, and instead of reshooting it all, I'm just going to do a hard cut and do exercise 45. So I was talking about how to solve exercise 45, and so here's our problem. We're doing the integral from 1 to 2 of 1 over x, and exercise 4.6. And so I think I explained where it came from, and now we're just going to talk a little bit about how to solve it. So as I try to solve it, what I'm going to do is I'm going to try to break it up into 4 sections. So I've got 1 to 2. Let's break these up into 4 sections. That means I've got 1.25 right here, 1.5 right here, and 1.75 right here. And then how I'm going to solve this problem is I'm going to draw 4 rectangles. And it's said to make each rectangle using the midpoint rule. So I'm going to use the midpoint of each interval to draw my rectangle. And then use the midpoint of that interval, and the midpoint of that interval, and the midpoint of that interval. Now, in order to estimate the integral, all I have to do is add those 4 rectangles together. So all I do is I just do the area of rectangle 1, which is f of that first point, which is halfway between 1 and 1.25. How do I find that? Well, I happen to know it's 1.125. But what if I didn't know that? I could just average them. I could do 1 plus 1.25 and divide it by 2, and that would give me my result. Okay, so we got that times the width, and notice our delta x here now is 0.25, so times 0.25. And now I do the middle of this section, and so what is that middle point? It's halfway between 1.25 and 1.5, which is 1.375. I'm going to put that in my function, and then I'm going to multiply that by 0.25. and then plus, I'm running out of space, so let's come right back here. Now I'm going to do halfway between 1.5 and 1.75, which is 1.625. And then notice my delta x's are the same every time because each segment is going to have the same 0.25 between those two. And then finally, my last one is 1.875 times 0.25. Okay, so there's all of those. Putting them in the function just means that I turn them into a fraction. So that means this one is 1 over 1.125 times 0.25. You know what, let's use the magic of the whiteboard to make this go a little bit easier. So this first one is 1 divided by 1.125. The second one is 1 divided by 1.375. This one is 1 divided by 1.625. And this one is 1 divided by 8.725. Isn't whiteboard magic great? And now all I have to do is compute all these. So I'm going to grab my calculator and see if I can do this successfully. 1 divided by 1.125 plus 1.375 plus 1 divided by 1.625 plus 1 divided by 1.875. And that gets that number and multiply them all. So I usually add these. I usually factor out my 0.25 and multiply it last. It doesn't really matter, but what I get for my answer when I calculate all this is 0.6912. So there's my result, and that's actually pretty close to what I know the answer, the actual integral of that is, which you'll find out in Calc 2 how to do an integral like this. We won't know how to do one like this in this semester. Okay, so that's how we estimate. The big things that I hope you're taking away right now, I know we've done a lot. I know it may have been a little overwhelming, but if you can do two skills, if you can use this idea of rectangles to solve problems, and you can find antiderivatives, if you can do those two skills, you're in really good shape. The next few sections, we're going to focus on the antiderivative idea of tackling these problems and working on and talking about integrals in that respect. For exercise 4.7 is an interesting one, but one that we're going to skip because it's not the most exciting thing that we just, but it's interesting, but that's fine. It's not something that shows up tons in later classes. Let me just make a few observations. Once we think of that integral as representing area, there are a few formulas that make complete sense. So if I have the integral from a to b of f of x dx equaling to some number, and that would be a picture where I have my picture here, and I have a here and b here. And the question is, well, what would happen if I were to switch the order? What would happen if I took the integral from b to a of f of x dx? Well, what this is we've broken it up into a bunch of rectangles, right? That's what we're doing. So think, every time you see these, think of this as we're breaking it up into a bunch of rectangles, and this dx is like this direction right here. This b to a just switches the direction that we travel, so now we're going here, and in a sense you could think of it as making all these dx's negative, and so this is negative whatever that number you got on the first problem is. So that kind of gives you a way of thinking about, a way of recognizing that if you just switch these two, if you switch the a and the b, you get the same answer but negative. And there'll be times, especially in your next couple calc classes, where that actually, it helps a little bit. It gets rid of a few negative signs. It makes life a little bit easier sometimes. What happens if I write down an integral from a to a? What should that be? What if I had an integral and the starting spot and the end spot was the same? Well, that would just be a picture where I started from here and then I went to here and I calculated this area. Well, notice there is no area, so that means this answer is always going to be 0. So anytime you're beginning, so if we did like the integral from 3 to 3 of any complicated equation here, e to the negative x squared, that's always going to be 0. It doesn't matter what you choose. If you have the same number here and the same number here, you always get 0 out for the answer. And finally, sometimes it's helpful to think about putting together multiple integrals or breaking up multiple integrals. So one option is if you go from a to b, and then you go from b to c, then what's happening there? Well, what happens there is that's our picture. We have A, we have B, and we have C. You have your picture, well, we have A to B. That's that first area right here. And then this is that second area right here. But what you'll notice is you can just glue them together and make one really big integral from A to C of f of x dx. So you can frequently take two integrals and stick them together, but I'll tell you how this is actually used most often. Most often we use it in reverse. Most often we have one problem that looks like this, and we split it up into two because the one problem maybe has something, maybe there's something crazy going on right here. Maybe at this point, our function comes here and does like a sharp point or something. Then we might split it up because this curve is pretty from here to here, and this is pretty from here to here. And so if we just split it up at that point, we've got two nice equations instead of one really bad equation. So this is what often happens in the future. But hopefully, but the important thing is that we're thinking of these integrals in terms of areas, and not only that in terms of areas, but in terms of adding a bunch of these rectangular spaces together. All right. Next time we'll be in section 4.3 called the fundamental theorem of calculus, and if that sounds important, it's because it is. One last thing before we're all done. 4.2 homework, I modified a little bit just to reduce it. So the homework is just do these 5 problems and I'll feel like you were successful on 4.2. So do 1, 5, 9, 33, and 35, and this skips those parts of section 4.2 that I skipped in the notes.